energized and ready to listen in on the last panel of the day. So, you know, as we kind of look at this question, you know, we've heard all about mobility blues and who do we sue and cybersecurity and public acceptance and all kinds of exciting stuff related to new technologies. And this panel is really going to try and focus on infrastructure and what infrastructure owner operators are needing to do to prepare themselves for the emergence of these technologies and how we, you know, deal with their safe testing and operations. So with that, we'll have a handful of presentations here, and then we'll go through a set of Q&A. So the first presenter that we will have here today is Joel Leitch, who is the owner of JPL Consulting. Joel has been engaged in transportation and traffic planning and design with an emphasis on urban freeway corridors and other high-type urban facilities for more than 50 years. He's been responsible for the planning studies of more than 2,000 miles of freeway, toll facilities, and arterials, including more than 900 interchanges in major metropolitan areas. Some things to note here: he is the primary author and editor of the ITE Freeway and Interchange Geometric Design Handbook, which I know a lot of engineers are very familiar with. And he holds a BS from Purdue University and MS in Transportation Engineering from Northwestern. So with that, Joel, take it away.
Well, thank you. Can we go on to the next PowerPoint slide? Yeah. In the 1950s and the 1960s, there was a great deal of research that was done in relation to driver experiences, characteristics, expectations. And that was translated, excuse me, into a lot of the design criteria that we have in our AASHTO policy. Can we go to the next PowerPoint slide? So, you know, the approach then, and if we're going back to the 50s and 60s and 70s, that the influence of human factors in relation to driver characteristics and driver expectations had a lot of influence on the geometric design and safety and traffic operations of our roadways. Next slide. So just some of these. The basic number of lanes, I'm only going to talk about freeways because that's probably going to be the first location where we're going to have CAVs. So this is from our AASHTO policy. The guidelines in relation to basic number of lanes. Can we go to the next slide? Also, this appears in the AASHTO policy as well. In relation to exits and entrances, that we have guidelines and criteria. Whether those will be as we look at it in the future, whether they will be appropriate, I don't know, but we have these in the existing AASHTO policy. Next slide. Also, in relation to the selection of the appropriate interchange, this appears in our AASHTO policy also. So in relation to tomorrow's guidelines in relation to the CAVs, is this going to be appropriate? Next slide. In relation to operational uniformity, in relation to the uniform aspects in relation to our interchanges, is this going to be appropriate? Do we need this? I don't know. Next slide. Signing. Do we need signing? This is a slide if you would drive outbound from Washington, D.C., and you're approaching the Capitol Beltway. Do we need signing in relation to the future? I don't know, but this is something that we need to consider. Next slide. Decision site distance. This is also in our AASHTO policy. Do we need to consider this in the future in relation to decision site distance? Or with CAVs, do we not need to consider it? Next slide. In relation to spacing between interchanges, this is from our AASHTO policy. Do we need to have significantly different distances between our interchanges if we have CAVs? I don't know. Next slide. So I'm not going to go through these, but you know, what is it that we need in the future in relation to the geometric design of our roadways? There is additional research, new research that is going on in relation to human factors, in relation to CAVs, and also human factors in relationship to the future of the operation of our freeways and motorways. Next slide. Well, so what do we look like in the future? Certainly we can increase capacity, most likely, and I've actually done some computations in relation to that. Certainly we can reduce crash reduction. So what should be the geometric design changes that we should or not make in the future in order to improve traffic operations with CAVs? That actually concludes my presentation.
All right, thank you very much, Joel. So why don't we go ahead and we'll hold questions until the end, and then we can kind of provide those to all the panelists. So as you can see here, obviously, when you talk about, you know, traditional kind of design efforts related to our infrastructure, there's a ton of considerations, you know, that'll be made to, you know, geometric design and signage and how we operate the roadways. And I think, you know, it'll be really interesting to see how, you know, these types of documents change over time to accommodate these new technologies. So excellent. So with that, yes, thank you very much, Joel. So the next panelist that we have here is Scott Shogun. He's the Vice President and the Michigan Area Manager of WSP USA. He is also a Senior Technical Specialist in Connected and Automated Vehicles. He has a diverse background in transportation planning, engineering, spanning over 2 decades. And he's been involved in CAV technologies for a while now in the mid-2000s. He helped lead WSP on a number of transformative programs, safety pilot model deployment, as well as some efforts related to the American Center for Mobility. Scott holds a BS in civil engineering from the University of Michigan and is a licensed professional engineer in 5 states. So with that, Scott's going to talk about some of the role of infrastructure that we see CAVs playing. So with that, go ahead, Scott.
Great. Thank you, Colin. Good afternoon, everybody. We can go ahead to the next slide, please. Great to be with you. This is a really important topic and one that we've had the opportunity to do a fair amount of research on recently and kind of advising to infrastructure owner operators. And I wanted to start with kind of some context, because I think this is an important piece to the puzzle, is really understanding, especially as you think about this from an infrastructure owner operator perspective. What are the goals of advancing infrastructure towards CAV adoption? Is your agency's approach to really be proactively enabling CAV adoption now, to get out in front of this to enable vehicles to more easily navigate your roadways? Or is it more reacting to the market, waiting for market forces to begin to push vehicles onto your roadways and understanding that? Is it more of a leading edge in terms of doing the things that can be done today in today's technology context for CAVs versus awaiting further development? We certainly understand that CAVs, the technology associated with CAVs, is going to develop further over time. The instrumentation and sensor suites are going to continue to be better. The algorithms to understand the context around you is going to continue to be better. Our agency is going to wait for that evolution and calibrate accordingly, or try to push things forward today. And finally, kind of prioritization of CAVs, versus enhancements to human drivers that can also support CAVs. And I think this is where you see kind of the sweet spot of investments that an infrastructure owner operator can make that can help all motorists today, in addition to helping CAV adoption into the future. And I think this is what we're seeing kind of emerging as the, as I mentioned, that sweet spot that is justifiable expense today that can support all users and move towards that future. But I wanted to, next slide, please. I wanted to really address some specific key areas as we talk about infrastructure. And I think Joel did a great job of kind of laying out the big picture questions related to geometrics, which are a huge factor going forward as we think about very high levels of penetration of AVs. But I think in the more near term, where much of our research is looked at, we've considered things like pavement markings. And this is one area that consistently in dialogues with industry and with the technology developers, this is a real high opportunity area that's very important for AV adoption. That's also very important for human drivers and to improve the roadway. And this is where I think we've seen the most evolution. The standards industry, the Manual of Uniform Traffic Control Devices, is moving forward recommendations to change standards around pavement markings in a way that would help support CAV adoption. as well. So we're seeing this push forward quite a bit. Next slide, please. Signage is another area that is talked about a lot and certainly looked at from the standpoint of can maintenance be improved, where we see foliage obscuring signs, for example, or see faded signs. What can be done to improve that? Are there standards that could be changed to make signs more machine readable? Greater use of symbology, things of that nature. But there's a big looming question as it relates to signs, and it's really what is the long-term need for physical signs as it relates to AVs? Will those be replaced with databases of sign information that will make the physical sign irrelevant to AVs, not to human-driven vehicles necessarily? Not that the signs are going to go away, but it's not necessary for them to be read by an AV anymore. And I think that really makes a path forward related to signage a little bit more interesting and brings in other questions there on the long-term need. Next slide, please. Work zones have also been identified as really a critical area related to AVs. One of the biggest challenges of certainly reaching any kind of a level 5 scenario is the ability to navigate a work zone effectively. There's a lot of guidance needed for AVs on the, essentially the travel envelope. Where are the lanes? Where are they getting modified from static mapping that may be available? Gathering data on where those work zone devices are and managing that data and disseminating that data. And a need to consider smart devices in the field that can basically self-identify a location and communicate that out. All areas that we see kind of evolving on the work zone front. Next slide. On the technology front, obviously, we talk about this frequently as it relates to connected vehicle technology. And clearly, we're in a time of flux related to that. There's a lot of concern over future-proofing that technology. And we're seeing particularly deployment and development of supporting infrastructure, understanding that some of the specific radio infrastructure may be changing over time here with some of the FCC actions recently. But there's also, I think, still a discussion ongoing of roles between the public sector and the private sector. How much of this does the public sector really need to own versus what is the private sector going to do for a multitude of reasons to support CAV adoption, including, in particular mapping assets, and how much of the systems are really going to be infrastructure-based versus more cloud-based data transmission. I think still questions that we're seeing evolve over time. Next slide. Dedicated lanes is a big topic. Apologies, these are the wrong bullets on this slide, but the concept around dedicated lanes, I think as we've talked about in some of the previous presentations, the challenges moving towards level 5 or even level 4 are very real. And a more controlled environment appears to us to be emerging as a likely path forward, even a necessity for advancing some level 4 deployment right now. So, but there's of course a push-pull with that. How much does the market need to lead that? What agencies could actually afford to dedicate lanes without significant deployment of vehicles, but how do you get the vehicles deployed without that? There's really a chicken and egg piece to this, but clearly dedicated travel lanes for AVs is a part of the discussion. And finally, next slide. Lastly, and this is an area where there has been some movement as well, is the impact of truck platooning. Really platooning of vehicles in general and even just AV operation on pavements. Bridge loading has been a big consideration when you've got close spacing of trucks. What does that do to bridge loading? And this is an area we're already seeing research. We're already seeing potential changes to standards around that to help modify how bridges are being built, because this is an expensive, long-term, long-life asset that will most certainly be affected by this type of technology. But even as simple as wear patterns and pavements, when you see very little wander within the lane from vehicles as they're being more precision guided, what does that do to pavements? And that's an additional area that's really being researched as well. So there's a lot of very near-term questions really related to this, and looks at how agencies have to consider investment in some of these different areas. So that is all I had for my presentation, and I will pass it back to Collin.
Thank you very much, Scott. So yeah, definitely some interesting considerations, that infrastructure owner operators are looking at. I mean, you have kind of those early wins, maybe with the static kind of sign lines conversation, looking at, more dynamic attributes, like work zones and sharing data. But then kind of the big investment conversations that may take place, like dedicating infrastructure to support these, or even the impacts to large brick and mortar investments like bridges. So definitely a lot to consider here. So thank you very much for the comments. So our next presenter here is Dr. Yihang Fang, who's the Assistant Research Scientist at U of M. Dr. Fang received his PhD from the Department of Systems and Industrial Engineering at the University of Arizona in 2015. His research mainly focuses on smart transportation systems, including traffic control with connected and automated vehicles, cybersecurity of transportation infrastructure, and CAV testing and evaluation. He has been the PI or the co-PI on multiple federal and industry-funded research projects, including the National Science Foundation, the US DOT, the US Department of Energy, as well as Ford Motor Company. So with that, Dr. Fang is going to talk about connected and smart transportation infrastructure. So take it away.
Yep, thank you, Collin, for the introduction. Can you guys see my screen?
Yes.
Okay, great. So yeah, it's my great pleasure to be here to attend this CCAT Symposium. And so today I'm going to introduce some of our work related to this topic, and I will mainly introduce this topic from a research point of view. Some of this research may not going to be deployed in short term, but in the long run, that is what we envision what this connected and the smart transportation infrastructure would be in the future, and how they interact with the connected and automated vehicles. So this slide actually shows a big picture of the transportation system, right? The current transportation system, as well as the future smart transportation system, have three main components. The travelers, vehicles, and the infrastructure. But the difference is their behaviors and the functions of the three components will change a lot in the future. So our research is mainly focused on intersection of the smart vehicles and the smart infrastructure. So mainly we want to tackle this from two directions. One is how to leverage the new data source and control capability from the CAV to improve the existing infrastructure operations. Because for the CAVs, we can consider them as either or both, actually, both a sensor, that is a remote sensor on the road, as well as an actuator, because now we can give guidance to the vehicles and also even directly control the vehicle trajectories. So based on this, if we consider the CAVs as a sensor, then from which we can collect the vehicle trajectory data, that actually greatly enhance the capabilities of the current infrastructure, the data collection capabilities of the current infrastructure. So we can do the CAV-based traffic signal optimization. More specifically, it's actually trajectory-based traffic signal optimization versus currently the loop detector-based signal control. And if we consider CAV as an actuator, we can actually control the vehicle trajectories. That actually expand our control dimensions from the only traffic signals to both traffic signals and the vehicle trajectory. So that we call this spatiotemporal intersection management. So this is the first direction. And the second direction is how to adapt the current infrastructure to accommodate new features of the CAV. So here we talk about actually, Joe and Scott both talk about the design, the redesign of the road geometry. And here I will give an example of this lane reassignment concept. And also when we have a very high level of penetration rate of CAVs, we may able to remove all the physical control devices that we call this signal-free intersection operations. And finally, another very important aspect of the future transportation infrastructure is the cybersecurity issue. We have talked about this in the morning session. So besides the vehicle, cybersecurity is very critical. The infrastructure cybersecurity is also very important in the future. So next, I will give some examples of our research or some other people's research related to this these topics. So I think you're familiar with this. Many of you are familiar with this Arbor connected vehicle testing environment. That's how we use connected vehicles as the mobile sensors to collect the trajectory data. So we equipped more than 2,000 vehicles and 70 infrastructure locations around the Arbor area to collect both the vehicle data in terms of the basic safety messages and also the intersection data in terms of the SPAT messages. And actually, if you're interested, you can visit this website. It's open to public, and you will see the real-time connect vehicle traces in Ann Arbor right now, and also the real-time traffic signal information. Besides that, we also developed some basic statistics like Q-length, vehicle delay, and time-space diagram, etc. But however, because of the COVID-19, we don't see much traffic on the road right now. So when we collect this connect vehicle data, then we can enable this trajectory-based traffic signal optimization. We designed a 4-step loop, including sensing, evaluation, optimization, and implementation. So we collect the vehicle trajectories as well as the signal data, and then we can draw the time-space diagrams from which we can directly see how many vehicles that stopped, how many times they stopped, where they stopped, and how long do they wait for the traffic signals, for example. And based on the evaluation, we can optimize the traffic signal parameters to improve the traffic efficiency. And then finally, we implement the optimized traffic signal timing plan on the road and then collect more data. And we continue this loop to iteratively improve the traffic management. Okay, so if we consider CAV as a actuator, then we can control the vehicle trajectories also. So then we call this a joint optimization of traffic signal parameters. And also we can either provide the guidance to the CAV trajectory, or we directly optimize the CAV trajectory as well. So there are two key concepts of this, or two main benefits of this. Is one is we can smooth the vehicle trajectories and reduce fuel consumptions and emissions. Look, this figure shows that now all the vehicles don't need to make a complete stop at the red signals, for example. And at the same time, by coordinating the traffic signals and the vehicle trajectories, we can actually increase intersection capacity by reducing the stop delay as well as the headways between the vehicles to further improve the intersection efficiency. And these two figures shows the two examples before the joint control and after the joint control. And you can see with the joint control scheme, all the vehicles pass intersection without stop. Okay, then if we come to the second direction, how the infrastructure should be adapted for the new CAV environment. One example here, this is a conceptual example, is the lane reassignment. Let's say if we have two type of vehicles, right? Through vehicles and left-turn vehicles. For the current road, we need to assign one lane for through vehicles and one lane for left-turn vehicles because they are conflicting with the other direction. But if they are CAVs, when actually they're approaching this intersection, if the vehicles can be reorganized based on their destinations. I'm sorry, the animation didn't show very correctly. These two vehicles should not collide with each other. So basically, then we can use both lanes to discharge the vehicle at the same time, right? So in that case, we can double the intersection capacity. Then another example is that the signal-free intersection where we have all the vehicles are CAVs. So the left animation shows the current traffic signal operations, right, by movements, and the right figure shows the signal-free intersection. You can see basically it's a reservation-based scheme that all the vehicles can pass the intersection on a negotiation type of strategy. And some research also shows that this signal-free intersection can greatly increase the intersection capacity as well. And finally, this the cybersecurity of the transportation infrastructure. This is a new problem because most of the current infrastructure is deployed in an isolated and independent manner, so that the cybersecurity is not that critical. But if the future infrastructure is connected to the outside world, then the connectivity may bring the cyber threats. So we need to investigate what is the threat model, what components are vulnerable of the infrastructure, and what potential attacks can be launched, and what are the consequences. And of course, we also need to design a defense system to detect attacks and protect the system. I think that's all I have. Thank you. So I will hand this back to Collin.
And the opportunity to do some things, increasing, safety and, optimizing capacity. I think it's a pretty exciting. So definitely another consideration and another attribute kind of the operations of the infrastructure that could potentially have a lot of value to folks. So thank you very much. So last but not least, I will present to you Dr. Weisong Shi. He is the Associate Dean for Research at Wayne State University and the Director of the CAR Lab. So Dr. Shi is a Charles Gershenson Distinguished Faculty Fellow and a Professor of Computer Science at Wayne State University. And he directs the Mobile and Internet Systems Laboratory and Connected and Automated Vehicle Driving Laboratory at Wayne State. He's an Associate Dean for Research at the College of Engineering, and he leads the Mobility Program at Wayne State. He is also an IEEE Fellow and an ACM Distinguished Scientist. So with that, Dr. Shi is going to talk about some of the things happening with edge intelligence-enabled smart infrastructure. So with that, take it away.
Thank you very much, Collin. It's a great honor to join this wonderful panel. And my background is from computer science. So in the next few minutes, I will share with you about more from computing point of view. So as a start. So here, some of you probably heard about that recently in the computing side. People talk about from the cloud computing to the edge computing. So here I'm using a figure to show you that this is basically the computing model right now. We already seeing some of them, and also in the next probably in the 10 years. So basically, you have this on the left side. You have this IoT devices, all kinds of the sensors, including the cameras, and as Yinhe mentioned, even vehicle itself we consider sometimes as a sensor if you're looking from the traffic management point of view. But then between the sensors to the cloud, in the middle, you have an edge. So here, the edge could be a vehicle itself, could be very powerful, provided the edge device. Also, the infrastructure, for example, roadside unit can be a very good edge server, depending on what type of application we are talking about. So here is a general view about the edge computing. So here is our vision about the future CAV. Again, from the computing point of view, but each of these vehicle, they're going to have this vehicle, computing unit, and they have multiple. As you can see, these two are kind of, the thin waist shape. So, for example, on the vehicle side, you have multiple sensors here, and then you have a lot of application is running on, on top of the vehicles. And also at the what we call X edge, you can think about as RSU, which is part of the infrastructure. Also potentially on the cellular tower provided by the telecoms. And then they also have their own, the data, for example, local traffic, local weather and the road conditions, etc. And on top of that, you have different applications. So in the next, here is the vision. In the next few slides, I want to talk about what's the challenges here in order to realize this kind of, smart infrastructure for the CAVs. So basically, we think there are 4 challenges here, CCSS. Now, the first 2 challenges are related to computing and the communication. So this figure comes from Intel, but this is based on the 2017 estimation. One of these autonomous vehicles each day can generate 4 terabytes of data. Based on the recent results, because the camera has become more and more high resolution and also the high definition of LiDAR. So today, if a autonomous vehicle running there, it could be generate 35 terabytes of data, and also the energy consumption is huge. It's more like a refrigerator itself, moving around. So this brings a lot of challenges to the computing as well as the communication, because it's data. If you want to talk into the infrastructure, and then you need the communication channels to support them. So that's the first 2 challenges. Now the third challenge here we call scalability, because you imagine that in the future you're going to have about millions of these vehicles all capable of communication, sending their sensor data, sending their video stream, also some of their for example engine data and etc. And as well as more and more rely on the HD maps. So they're going to building this real-time map sending back. So this is going to create a huge scalability issue to the infrastructure. So today's infrastructure is not really ready for this type of communication and then this data exchange. So that's why this is the third challenge. The last one, I don't want to put in too much effort here because Yinghen already mentioned that, which is the security. Because once you start putting more and more computing and the decisions made on the infrastructure, then it became more than before that's the importance of the security. For example, attacker right now could attack the infrastructure very easily, and they can attack the computing devices. As you see from the news that there's a vehicle, a Chrysler Jeep was stopped in the middle of the driving, and also for the communication channels, there's also challenges here. So those are the 4 challenge areas. So in order to understanding about where we are today, so we recently had done a research trying to understanding about the end-to-end, the latency from the communication. So we basically evaluated the Wi-Fi, the LTE network, and the DSRC that dedicated short-range communication, supposedly used for the vehicle talking to vehicle and the vehicle talking to infrastructure. And then here I'll show some results which will be published a couple of months later. So, for example, on the left side, you see the latency. You will see that today's, again, is based on the hardware we have. You can see even sending a basic safety message out using LTE network is 3 milliseconds. If you're talking about sending an image from the vehicle to the infrastructure, the latency is more than is 1.7 seconds here. So there's the latency today is basically we found out that it's not really ready for support any type of the applications running on the CAV today. So although we are very excited about that the vision presented here. So we also look at the overhead of the computing equipment, running on the RCU and the OBU. As you can see that the memory part, the OBU part, this all, how do you read from this data is, all this is a cost. Because imagine that you're going to run a program here, need a huge requirement on the computing devices, then the cost for the computing equipment, the cost for the communication equipment, it will be huge. So without address these issues, you can't really move on to the real, the vision of the CAV. We also talk on the left lower part, we show that how the latency relates to the speed. Many people talk about the DSRC and then Wi-Fi, but if you think about we even very slowly moving, you can see that the latency is increased significantly. Once you're running, imagine that you're running in the highway, well, that's going to be even, the latency and the reliability will be an issue. The last thing we compare with the power, the energy consumption here, and basically you show that the center side and the receiver side. But basically here we found out that today is where we are is we have insufficient, unstable bandwidth with non-negligible power dissipation and the system overhead. So that will be the obstacles that for the real CAV applications. So without solving this, we are not going to see any real deployment for the applications here. And then here goes to what's the real problem that we need that we think is worth for the people, particularly for the audience from the computing side. How can you co-design the computation communication in a secure and scalable way for the CAV scenarios? That is one of these, the challenges that we are facing. So I use the next few slides to show that what we have done. So in our lab, we have built a edge server, which is capable from Wi-Fi, DSRC, LTE, and 5G. We call it Equinox, and then it's talking to this vehicle, and then we run all these different kind of computing devices running on the OBU, and also we evaluate the different computing devices running on the edge. It's more like a roadside unit, and then we're using this platform to run these experiments. And then in addition, we also built this HydraOne, for the indoor. Although it's an indoor like a robot, but it's come with all this standalone kind of camera lidars. So this allows us to do the research. It's an open source research and education platform to support this type of research and education activities. And the last thing I want to make sure I want to cover here is eventually this intelligence are going to be deployed on this edge. For example, at the on the vehicle as well as the infrastructure. Because of this huge amount of data is generated at the edge, and then it's impossible for the infrastructure to ship all this data back to the cloud. So that's why traditional cloud, you have this algorithm, software, and hardware. And now this is on the right side. You can see that this is basically what all these pretty much hardware companies, they are trying to come out with the small edge-oriented devices, so that this is going to be running on the for example, running on the vehicle as well as the infrastructure to support this type of intelligence. And just now, Yingheng showed several examples that this could be, very good example to leverage this kind of intelligence. So that a couple of real projects that our group have been working on. One is funded by NIST, is through the MIT Lincoln Lab. So basically, we leverage this the vehicle as a computing. So talking to the law enforcement, the body camera, talking to the vehicle connects to the infrastructure and make some real-time decisions. So the other one is we're trying to leverage the multiple intersections, multiple vehicles. How can we do the collaborative learning together? So this is another possible application for the CAVs. And the idea is you're running multiple learning components on each of these vehicles. In this way, you don't need to sending all this data back to the server, which is a huge cost for the truck companies and for the OEMs. So instead, you keep all the data here for the privacy purposes to reduce the latency and the bandwidth requirement, as well as you can do the customize for each individual drivers. And then you can training the model. So I will skip this. So basically, the idea is you can, doing this on the edge and then talking to the infrastructure, and then to make sure that all this data will be keeping on the edge side. I think I will stop here. Thank you so much.
All right, great, Dr. Shi. So obviously, you know, as you talk about some of the opportunities, you know, that may exist with edge computing, obviously there's some considerations associated with, you know, the challenges as well, you know, with data computation and transfer and scalability and all these things. So great comments. So now we'll jump into, you know, kind of the panel discussion. I mean, we've heard about, you know, kind of the traditional design and what needs to change in regards to that. You know, what near-term investment opportunities may exist, you know, how folks are researching, you know, optimizing infrastructure to support these types of technologies, and then, you know, the opportunities that exist with all the data and things that we could be doing, you know, from a safety and efficiency perspective. So I guess we'll start here actually with a comment that was made. It's a comment and a question that was made in the QA here. This is from an anonymous attendee. So since the late 2000s, a lot of automotive suppliers and special interest groups have promoted connected vehicle technology for governments and OEMs to adopt. After a decade, we saw automated vehicles kind of in the same light. So even though neither technology has a good business case to deploy, stakeholders from both have been asking governments and infrastructure owner operators to invest heavily in new infrastructure research and installations. So with that statement made, now it is more evident that we will not have much deployment of level 3 AVs because there's a technical gap and an unwanted benefit, or CVs, you know, through the challenges with the FCC or the lack of benefit. So is it time for infrastructure owner operators to reconsider the source of driver and traffic control benefit to not come from direct communications or automated vehicles? Do we have any thoughts there? Is it time for IOOs to reconsider, you know, the source of driver and traffic control benefit to not come from direct communications or automated vehicles? I'll let the panel provide their thoughts, and then I can respond as well.
Well, I'll start. You know, from a practicality standpoint, most likely the first application of CAVs is going to be on controlled access facilities. For instance, here in Northern Virginia, it would be the easy pass lanes. In Houston, it would be the toll lanes. In Denver, it would be the application of CAVs on the toll lanes. So that's where I see the first opportunities to really apply CAVs and initially have them interact with other vehicles.
Thank you. Any other thoughts here?
Yeah, Collin, I'll jump in, I guess. You know, I think Joel started to touch on it, but I think what we saw, you know, particularly maybe 5 years ago, was, I think, really still this kind of moonshot approach, where it is, you know, we are going to imminently be at level 5, and we have to have, you know, the kind of the infrastructure all sorted out to support that. This, you know, almost frantic race to meeting level 5, and I think we've, you know, obviously seen in the last several years that you know, this is really hard. This is a long path to get there. So, you know, I think there's been a recalibration towards, there's no way there's going to be a broad infrastructure solution to meet a you know, demand on all roadways. It's got to be more of a defined use case, a defined location type of application. I think that's going to have to be the catalyst, and it seems that that is where the energy is shifting to now, from my perspective.
Yeah, I would agree.
Any other thoughts?
Yeah, I'm gonna say a few words too. So I think a more feasible path is still the, we call the cooperative automation, that I think the communication between the CAVs and the infrastructure is essential, but the automation capabilities should be shared between the CAV and the infrastructure. As Scott mentioned, that just the level 5 is a really difficult job to implement. But if the infrastructure has some levels of intelligence, I know there's a project called the InfraMix, sponsored by the European Union. They kind of define different levels of infrastructure intelligence from zero, like level 0, the current infrastructure, to level A, to like to support cooperative driving. So some of the functionalities from the vehicle side, for example, some of the perception tasks or some of the task planning tasks, if those tasks can be shared from the infrastructure side, that actually provide a more flexible path of deploying the CAV system. So if you have a higher level of CAV, you may need less infrastructure support. But if your infrastructure is well equipped, so you can also deploy a low level of CAV. So that may provide a more flexible path.
Okay, I can add a few things which I observed in the last couple of years. You know, I'm not really a civil engineer, so I think Scott and Joe, you guys are experts. But I have a feeling is that the usually is taking a cycle for the civil engineer and for the transportation folks to change the, for example, the traffic signal and this, right? Because this is it's not like a computer software. You can deploy some update, every day. So this is like once you deploy it, it may take like 20 years for you to update. My feeling is that right now might be a very good time that for the people to starting, add the new functionality to the traditional signal systems, because signal has been there for a while. And a particular case is, for example, when I was in China last summer. So when some of the cities, because there was a very old technology has been used, but then when they started build the new one, they all of a sudden deployed all this kind of 5G, and then they come out with these computing devices, all come to this. So when I was in Hangzhou the other day, and then I noticed that their infrastructure is already being adaptive signal. So what happened is that during the, you see my background is from my office view is a woodwork. But I noticed that this is every day after 9 o'clock, normally it's pretty much is empty because there's not many traffic. But then during the morning is one-way traffic in. During the evening is another traffic is getting extra to Detroit. But in Hangzhou in China is different. What happens is in the morning, 6 of the lines among this, if you consider 8 lines there, and then 6 of lines will be getting in the city. During the evening, and then another on the 6 on the opposite side is already being there. So this has been already deployed there. So I think that it's a opportunity right now because of that my background, that was when woodwork was reconstruction in the last 50 years, right? The first time. So this is an opportunity that they can start putting the new things there. So that I don't know if I answer the question, but I just might believe that
no.
it is a good time,
Yeah, no, I think everyone answered it in some way, shape, or form. I think what it boils down to is that, me being an infrastructure owner operator, I think, yes, we have to be careful that we're not, investing in the next, shiny object. However, we do have to be thinking about, opportunities as we're upgrading our infrastructure to be future-proofing it for, opportunities to support connected vehicles and automated vehicles. And so I think, what we're seeing is some of these low-hanging fruit opportunities potentially emerge, and things that we can do to invest in today that may help, in the future, even though we know that things are a little fuzzy. but we think we can make investments today. Excellent. Well, we have a couple other questions here. We'll try and hop on these. One of them is, do we envision P3s for communications infrastructure deployment? Are you seeing this happening? You know, if so, how?
I can grab this one. Short answer, yes, totally. Am I seeing it happening? No, not yet. And I think that really gets to kind of the, you know, really that national, I think if we had already seen a national directive on specific technology for connected vehicles, I think we would already see an industry well underway and developing out. Because I think if you look at what does it take to create critical mass for benefit, you have to front load it with a large scale deployment that almost no agency can afford to do. So, you know, are there public-private partnership opportunities where there is a turnkey, you know, deployment and maintenance type contract that's, you know, that is kind of developed and, you know, paid out over time by agencies that would allow kind of smoothing the cash flow piece of that to provide you know, a large scale deployment? I absolutely see that being something. Is there a data angle there that could benefit and offset some of the IOO cost to make a P3 work? Absolutely potential there too. So I certainly think when we really see a direction, a consistent direction nationally on this, personally, I think that's an industry that's going to happen.
This is Joel. I think the first opportunity, as I described below or previously, is that on toll lanes, there is an opportunity to investigate the combination of CAVs and you know, regular vehicles. And I think that's the first opportunity to really investigate. And we're talking about that here in Northern Virginia on Interstate 95 and Interstate 395 and the Capital Beltway.
Excellent. So why don't we take one more question here that's been posed, and then we'll probably hand it back over. So how to take pedestrians into consideration in infrastructure design for AVs and CAVs? What kind of changes can be made? Any thoughts?
Well, it's a serious problem in relation to pedestrians. In Israel, in Jerusalem, the first person was killed with a CAV was a pedestrian. So, you know, that's an issue that really needs to be addressed.
Other thoughts from the panelists on things they're aware of that are happening on the infrastructure side from a safety perspective?
Yeah, so one of the ways probably is to build the CAV, like a dedicated region, dedicated lanes, dedicated area that entirely separate with the vulnerable road users. But that will cost more investment. In the infrastructure side, for example, we need to build more overpasses or underpasses for the pedestrians.
Yeah,
all right.
Maybe I'll just jump in on that real quick, Collin. Yeah, and I think that's I wish I could say I had a great answer, but I think it's more identifying the problem. In that I think if you look at urban areas today, the trends in infrastructure that you're seeing is more of a shift towards shared streets and, you know, really blurring the delineation between pedestrian space and vehicle space. And the reality is that will make it very difficult for AV navigation in those areas. So I think you're going to see a tension there in urban areas between how to facilitate AVs while not compromising, really kind of non-motorized transportation in those areas. I think it's a big challenge the industry has to figure out.
All right.
Right.
Well, with that, we're right up against it. It's 4:40, so I think we're at our hour. So I just wanted to say thank you to all of our panelists for their time and their information they shared. Thanks to CCAT as well as all the attendees, that have stuck around to kind of hear what we have to say.